Welcome to this session of Shadow the Scientist. My name is Jamaica Marshall, and I'm very pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is an initiative housed under the Creating Equity and STEAM umbrella of programs offered by TEAM at the University of California, Santa Cruz. In this session, we have the privilege of shadowing a stellar team of astronomers. Now, they'll be using the multi-object infrared camera and spectrograph MOIRCS on the Subaru telescope, which is an 8.2 meter optical infrared telescope located near the summit of Maunakea on Hawaii, which is operated by the National Astronomical Observatory of Japan. Now, they're going to be targeting several suspected large structures of matter, which was under formation where the universe was less than 15% of its current age. And we can hear more about how they were able to estimate that, hopefully a little bit later in the session. Now, these structures are some of the most massive found to date in the early universe. And the team tonight will be exploring and mapping them in depth. Now, let's quickly go to our team to get us started with some quick introductions. Now, just before we do that, though, I will say that observations are currently underway, and so we'll be meeting with just a few of the team members, and the rest will join us. Will be able to engage with us a little bit later. So perhaps we can start with Ben. Welcome. Brief intro, please.
Thanks, Jamaica, and thank you everyone for joining. Yeah, my name is Ben Forrest. I'm an assistant researcher at the University of California, Davis, and I've been working as part of this collaboration for the last it's a little over 3 years now. As Jamaica said, looking at these very massive structures in the early universe, identification, follow-up, and characterization of them. Yeah, thank you for joining.
Thank you, Ben. Now let's move to Ekta Shah. Ekta, welcome.
Thank you, Jamaica, for introducing me, and thank you everybody for joining. Sorry, got disturbed by cat. I just finished my postdoc at University of California in Davis, and then I moved back to my home in India. So currently I'm joining from India, as you can tell from this sunlight. And I have been also part of this group for last 3 years, little over 3 years. And so we are all kind of studying the big structures in the universe, and I will tell more about them in a bit. But I'm particularly focusing on how these structures affect properties of galaxies, like their star formation, their black hole activity, and many such properties. So I'll be happy to tell you about them in a bit. But yeah, thank you for joining.
Thank you, Ekta. We definitely look forward to hearing more about all of that in detail a little bit later. And another member who can join us and give an intro right now, excuse me, is Dr. Roy Gal. Roy, hello, welcome.
Aloha. Thanks for hosting, Jamaica. My name is Roy. I'm an astronomer at the Institute for Astronomy here at the University of Hawaii in Manoa, which is in Honolulu on the island of Oahu. I've been working on looking for galaxy clusters for the past 25 years, starting relatively nearby and moving further and further out as our capabilities to explore the universe have expanded. And I'll talk to you a little bit about the observatories on Maunakea and Subaru and our capabilities here when we're all POW. Well, POW is Hawaiian for done. When we're all POW with our introductions here.
Excellent. Thank you so much, Roy, Ekta, and Ben. Now, we do have several other members of this amazing stellar group of astronomers with us this evening, but they are currently engaged in doing some focusing and targeting with the telescope right now. Brian Lemaux, who you can see in one of the windows, as well as Dr. Kodama. So we'll hear from them in a little bit. I'd like to go back to Roy now to get us started with some background on Maunakea and the observatories that are located near the summit. Roy.
All right, mahalo, Jamika. So let me tell everyone a little bit about Maunakea and telescopes there and try to do a sort of, I don't know, 5-minute or so history if I can. So I like to start with this image, which is from space. The stuff you see at the bottom of the image is parts of the International Space Station. And this is a picture of the big island of Hawaii from space. So we are right on the peak there on Mauna Kea. This picture was actually taken by an astronaut, Ed Lu, who worked at the University of Hawaii for a few years. So it's a sort of, he's looking back at his temporary home. And the islands of Hawaii are the most isolated islands inhabited islands on the planet. They're also very smooth sloping volcanoes called shield volcanoes. And that isolation, the darkness on the big island and the smoothness of the volcanic slopes and the altitude where telescopes are at almost 14,000 feet altitude, so over 4,000 meters or so, makes for an incredible, so the best observing site in the Northern Hemisphere and potentially the entire planet. And in terms of the history of astronomical telescopes, a quick look back, the sizes of telescopes are determined by how big the mirror is. Or in the past, it used to be lenses. Today, we use mirrors. And when we talk about like Subaru having an 8.4 meter mirror, we're talking about the diameter of the mirror. It's like having an eyeball 8 meters across. But we haven't had telescopes that size until the latter half of the 20th century. So here's some of the biggest telescopes in the world looking back into the 1900s. And you can see in the mid-1900s, the biggest telescopes we had were like the 5-meter telescope in Palomar, California. But today, we have a large number of large telescopes around the world. But the reason we have large telescopes on Mauna Kea is a little bit of an interesting history, which I like to share because it's very unusual. Today, we know that telescopes go on high mountaintops, but the first observatory on Mauna Kea only opened in the late 1960s, which is relatively recent compared to the ones I showed on the previous slide. And the reason we have telescopes on Mauna Kea is sadly, in a way, because of a natural disaster. So in 1960, there were no telescopes on Mauna Kea. There were no big telescopes in Hawaii at all. And a tsunami devastated the town of Hilo on Big Island, on the island of Hawaii. And the Hawaii Island of Chamber of Commerce was trying to figure out how to bring businesses back and how to revive the economy. And the leader of that group, Mitsuo Akiyama, knew that telescopes were built on mountains, but no one had built any on a summit as high as Mauna Kea. But he thought maybe astronomers could come and create jobs and industry on the Big Island. And so he wrote letters to astronomers who operated observatories. Most of them thought he was crazy to build the idea of building telescopes at that altitude. But one astronomer, Gerard Kuiper, whom some of you may know, is famous for the Kuiper Belt, which is where Pluto has been demoted to. And he was at the University of Arizona's Lunar and Planetary Lab. And he came out to Mauna Kea and checked it out as a site. And that was in the late 1960s. At that time, the University of Hawaii had no astronomers, zero. And UH hired an astronomer from Australia, John Jeffries, a solar physicist, actually, to come and sort of kickstart the program here. And testing of the site up on Mauna Kea in the mid-60s showed that it was the best observing site that anyone had basically ever witnessed. So after that, people started to build observatories on Mauna Kea, and today it's host to many of the biggest telescopes in the world. And I skipped over a lot of the history. And what you see here is the Keck telescopes, which are 10-meter telescopes, and the Subaru and Gemini telescopes, which are 8-meter telescopes, which are the biggest telescopes on the mountain right now. And in comparison, here's all the mirrors of the optical and infrared telescopes on Mauna Kea. The University of Hawaii operates an 88-inch or 2.2-meter telescope. That was the first big telescope opened on Mauna Kea, opened in 1970. And you can see the size of the telescope that we're using down here in the bottom left. And all these other telescopes are operating. Actually, this small one in the top left has been removed from the mountain recently. So these are quite large mirrors. You can imagine a mirror 34 feet across or so. No, 8 meters times 3, so about 27 feet across. It's quite a large size mirror. And to put that in context, these are all the big telescopes in the world today and some planned in the future. So we're using this one, blue one right here, the Subaru telescope. Oh, I didn't mean to glue these sides, so let me skip that. All right, so that's where we are. We're up on Mauna Kea with all of these telescopes. And I just wanted to give you a taste of what it looks like today. So let me show my web browser. Here we go. So we're up on Mauna Kea, and we can actually see with webcams what everything looks like up on the summit right now as we are observing. So if you're online, if you Google Mauna Kea Weather Center, then we have a specific place at UH that does nothing but forecast the weather conditions for the summit of Mauna Kea. And you can see cameras, and these, even though they look like daytime images, they are actually nighttime images from high sensitivity cameras. So here, for instance, is a picture from the adjacent to the telescope we are at. This is the Subaru telescope dome. The telescope is inside the cylinder, and it's a kind of almost fisheye camera looking straight up. These two white things here are the two Keck telescopes, and you can see our sky. You can see what I think is the moon and some of the stars. So this is the sky up on Mauna Kea right now. So you can check that out for yourself on the Mauna Kea Weather Center. And astronomers, of course, want to know if the skies are clear, if the weather conditions are changing. And we can actually check all of the current conditions. The observatories have wind speed monitors, humidity monitors, and all kinds of things like that. And right now we see the winds are pretty calm. The humidity is low. There's no danger of getting condensation on the mirror or anything like that. So it looks like a good night of observing. And when we take images, we'll be able to measure how good the image quality is, how blurry it is from the atmosphere right now.
On the instrument display, I see a position angle of 45. Is that not correct?
Okay, and then you can hear in the background, that's my colleague Brian. They are busy setting up the telescope. And I don't know, Jamika, if you want to switch to his screen. They are currently busy focusing the telescope. There was a team using the telescope in the first half of the night, and our team is using it in the second half of the night. So they were doing a switchover and setting up for our observing program so that they refocus the telescope and make sure the camera that we're using works. And just as an extra bit of background, when we talk about the telescopes and the big mirrors, that's important. Those are like giant eyeballs. They collect a lot of light, right? Our eyes open up bigger as we, our eyes open bigger when it gets dark. And you can imagine if your eye could open to be 30 feet across, you could see things that are pretty dim. And that's what we have as our big telescopes. But to collect that data and make sense of it, we have special cameras, or what we call instruments, attached to the telescopes. And every telescope has the mirror and then the various cameras. And we pick the camera that we're using based on the science. And we're looking at infrared light tonight. Maybe Ekta will tell us more about that. It's part of the science. And we're breaking that light up into, we're picking out specific colors of light to observe with a specific filter where we're trying to find galaxies at a specific distance from us. So I think that's all I wanted to say to give a little bit of background about the telescopes here. And then I think Ekta has some slides to share about the actual science that we're trying to do tonight with these giant eyeballs.
Yes, thank you so much, Roy, for that fantastic introduction to Mauna Kea and the observatories. Ekta, lead us into the science that's happening.
MOIRCS displayed, if not in the main instrument display, the main telescope.
I will
I'm
take
happy to do that.
In your beat,
Let me share my screen real quick.
I still didn't understand. It's not displayed. What's the relationship between the cast rotator angle and the and MOIRCS?
Okay. So I think let me get started.
This one here.
Jamika, are you there? Yeah, okay, perfect. Brian just muted himself.
I am. Yes. Okay. Yes, I just.
Okay.
Mhm.
Awesome. So what we are going to observe today is a really big structure that I will describe just in a bit. So before we get into that, let me give a little bit of background. So most of you might have already seen this picture. It's of galaxy cluster taken by JWST. And as you can see, in this kind of systems, there are lots and lots of galaxies that build one big system. And let me go. So galaxy clusters are basically big structures where lots and lots of galaxies come together. And as you can see in the simulations, I don't know, can you guys hear the background sound? Sorry.
Yes, we can
dramatic.
definitely hear that.
Okay. So I don't think you can hear this sound in space when this is actually happening, but at least we can add some dramatic effect. So here we see kind of gas distribution and a little bit. Okay, and what happens is over time, through this gas and through the gravitational effects on the gas, this kind of galaxies get built up, and these galaxies themselves kind of move in this large gravitational well, and they can kind of come together and create this large structures that has lots and lots of galaxies in it. And as these galaxies are moving in this potential, you can also see that their shapes get disturbed. A lot of gas can come out of them and create this kind of tidal tails, and this entire process can also affect a lot of other properties of galaxies. So so this was simulation. So basically our idea, not just our idea, but kind of our theory of how the systems can be formed. But of course, when we look at the actual universe, we don't see this process happening in real time, right? Because it takes millions to billions of years. So we see this kind of static pictures where we do see lots of galaxies together. So here is another picture of a galaxy cluster. And it's very important to kind of understand, like, how the systems are forming and evolving over time. And to do that, first of all, we need to identify like which galaxies are part of this system, because as you can see, there are lots and lots of galaxies that may seem like they are together, but in 3 dimension, they may or may not be part of the same system. So let me also say a little bit about why we want to study these kind of systems. So one thing that I showed during the simulations is in this kind of clusters, the shapes of galaxies can change a lot. So when we look at clusters in the nearby universe, we see less number of spiral galaxies in them and more kind of elliptical galaxies. So the shapes of galaxies can change a lot depending on what kind of environment they live in. So if they live in cluster kind of environments where lots of galaxies are together, you see more elliptical galaxies. If they are kind of more isolated, then you see more spiral galaxies. On top of that, so apart from changing the shapes of the galaxies, the environment can also affect other properties, like I mentioned. So one of the things that can also happen, so as we were looking in those simulations, many galaxies kind of can come together and merge with each other, which can affect the total mass of the galaxies. So what we do see in the nearby universe is most of the massive galaxies in the local universe reside in galaxy clusters. So it seems like through this kind of galaxy mergers or other processes, lots and lots of very massive galaxies get built up in this galaxy clusters. But one of the things is also that when we look at this massive galaxies, they don't seem to be forming many stars. So then the question is also like, how did they build up this kind of mass? Is it just through galaxy mergers, or did they have higher star formation rate in the past? What was their formation history like? How did the environment affect their formation? So there are lots of questions that that has to be answered. And along with this kind of building up the mass of the galaxies, there are also other properties that can be affected by environment, like the overall star formation rates of galaxies or the black hole activity itself. So, so we want to study kind of how this massive systems of galaxy cluster formed and changed over time, how they affected the properties of their constituent galaxies over the cosmic history. So we are interested in the formation phase of these galaxy clusters. And when they are forming, we call them protostructures or protoclusters. And so that's what our team kind of studies. And for that, we actually, our team is called the C3VO team, or the Charting Cluster Construction with Woods and Orals team, because what we do is we use this C3VO survey, which identified lots of potential galaxy protostructures in three different fields. And what we do is we identify them using a method that I will describe in a bit. And then we target them further using different instruments on the Keck telescope to then for confirming that there are actually massive systems, and to well characterize them, and then to further study them. So let me say a little bit more about the process. So like I said, we see when we take picture of the picture of some area of the universe, such as this picture, you see lots and lots of galaxies. But in reality, when you actually look at the three-dimensional positions, what happens is, if you get that third dimensional info, then many of them can have very different positions in the third dimension, right? So what we want to do is we want to identify which of the galaxies are not just close in 2 dimension or the projected dimension, but they are also close in the third dimension. So they are actually part of a large cluster itself. So they are actually kind of together in the third dimension, and they live in this very dense system. And to do that, clearly we need this information about the third dimension, so we can rule out galaxies that are far away from some structure, and identify galaxies that are together. And for that, we take the observations that we are kind of taking today. And what we do is we divide the region of sky in different slices, and then we kind of estimate the, just 1 second, huh? So what we do is we divide the region of sky in different slices, and in each slice we look at we estimate the density of the galaxies. So if we have galaxies together, so we use this method called VMC method, and we divide the region of sky in different cells. And if the size of cell is smaller, then the galaxies are together. And if the size of cell is bigger, then the galaxies are kind of far away. So this kind of gives us a mathematical way to characterize the environment of galaxies and to measure its overdensity. So through this, we can actually kind of get a distribution of cells that have overdensity that is more than some threshold. So for example, more than a factor of 2. And through that, we can kind of get the three-dimensional shapes of the structures. And using that, we can also estimate the mass and shape and other volume and other properties of this three-dimensional structure or the protostructure. So I hope that kind of made sense. And using this method, we have identified lots of structures as a part of the C3VO survey. So here I have shown some of the structures that I have discovered. And apart from this, apart from these structures that you see here that span a wide range of redshift or time in the cosmic history, these structures are very, very massive. So each of these structures have a mass of more than 10 to the 14.8 solar mass. So yes, I'm trying to say, what do you call it? Hundreds of thousands and hundreds of thousands more suns. So it's hard to comprehend, but these are very, very massive systems that have lots and lots of galaxies in them. And so we have characterized the shapes of this structure. And what you see in this picture is kind of, again, the overdensity that I just described. So the red regions are highly dense regions and the blue regions are relatively less dense regions. And one thing is, if you, they kind of look very weirdly clumped because they are still in the formation of, in the process of forming, right? So they don't look very nicely spherical. So you have this kind of clumps that come together and are making this structure. So over the time, the shapes of these structures can also change. So this is, again, it's important to think about these systems as kind of dynamic systems that change with time, not on human time scale, but on cosmic time scale. So apart from these structures, we have also identified lots of other structures as a part of the C3VO survey. And today we are observing one of the structures in the cosmos field. So cosmos is one of the very well studied extragalactic field, and here is its area on sky. So it's a large field, and that has many, many different types of observations across the multi-wavelength regime that help us kind of conduct very deep extragalactic studies spanning different kinds of scale and different kinds of science. So in this field, our colleague Ben Forrest, who is here, has discovered this structure Alentari, and what we are trying to do is we are trying to better characterize some parts of it. So maybe, Ben, if you have time, would you like to say something about this?
Sure. Yeah, I can just give a few words on the structure itself. So I think Ekta, you're going to be talking about the methodology we use to identify these structures. But yeah, this particular structure we discovered a few years ago, and one thing that's pretty neat about it is that we actually discovered it using two different methodologies, which is one thing that's always very important in science, is to test things with different methodologies and try and replicate results to confirm that the results are robust and not just an effect of some statistical error or methodology error in a single study. And so this particular structure we identified through the C3VO team as in the method that Ekta will talk about with this VMC. But we also, in part of another survey that I'm a member of, we were searching for very massive galaxies in the early universe. And so these are galaxies that have as many stars and more than the Milky Way does today. But they formed all those stars in the first 1 to 2 billion years of cosmic time, whereas our Milky Way has taken 13.5 billion years to form that many stars. So these are very massive galaxies very early in the universe. And one thing that we are interested in as part of that survey was to characterize the environments in which they live. Do they preferentially lie in some of these overdense structures, or maybe not? And so a couple of these very massive galaxies that we confirmed the distances of do lie in this structure. And we also confirmed that there were lots of neighbors around them. So it's a kind of neat structure in that we have these two methodologies that are coming to the same conclusion about the existence of this very massive structure in the early universe. Yeah, back to you, Ekta.
Awesome. Okay. Just 1 second. Yeah, so what we do is, so basically, like I said, that what we want to do is we want to identify which of the galaxies are part of the system and which galaxies are not, to better characterize the system. And for that, just to give an illustration, what we sometimes use is kind of this kind of mask. Okay, so this is a part of a very different instrument on a different telescope. So basically we have this kind of protostructure. So this is an image of a large protostructure called Hyperion, and here you see the overdensity distribution. So what happens is, as you can see, when we have this kind of picture of sky, again, there will be some galaxies that will be part of the system and some galaxies that kind of, it may look like it's in the same area, but you do need that three-dimensional information, and then you can rule out that these galaxies may look that they are in the same system, but they are actually very far in the third dimension, right? So what we actually do is for Keck telescope, which is another telescope in Hawaii, for on one of the instruments, what we do is we kind of create this kind of masks. And as you can see, there are slits in it. So hopefully you can see the small slits. And what happens is, let me really put this. So what happens is when you have galaxies in the background, so we arrange the positions of the slits where the galaxies are. So if you want to target some of the galaxies, you kind of put slits on the galaxies that you want to observe. So the slits will be on top of the location of the galaxies, and then the light from the galaxies. So as you can see, there will be kind of light coming from the galaxies. That will go through the slit and through the slit to the instrument, and the instrument will then divide the light into different parts, and that will give you information about how far the galaxy is, what is its composition, and other properties of the galaxies. And you can use that to determine which of the galaxies are together and which of the galaxies are far away from whatever system you are trying to characterize. So this is the actual mask of the DMOS instrument on Keck. And here is another mask that we had designed to observe one of the structures that I showed. Different kinds of instruments can have different sizes. So it can target different size on the area on the sky. And you can also kind of modify. Some of the telescopes also allow you to modify the size of the slits. So if you have like very large galaxy, you can, choose the size of the slit accordingly. So there are many different things you can do. So these are kind of like multi-object spectrographs that allow you to observe lots of galaxies together. Okay, so that concludes this part. So this was kind of DMOS. And today we are observing using MOIRCS instrument. So what we can do is, I think if you guys can share the screen, and we can talk about like what are the different things on the observing screen. So we can talk about that.
So I can highlight Brian's screen, but I believe Dr. Kodama was potentially going to share his screen if possible. Roy, do you know?
I don't know. I just unmuted to say that, I'm happy. I'm probably Ekta. I guess I shouldn't speak for her. We can answer questions about the telescopes or the science or things like that. I don't know how you're taking questions, Jamika. If people should just put it in the chat, or if yeah, right. I don't believe they can unmute themselves. So I think they'd have to put it into the chat.
Yes, I put that a little bit earlier, but yes, please put your questions and comments in the chat for us. And maybe perhaps we could start off with the instrument that's being used for the current observations. MOIRCS, Ekta, Roy, Ben, would either of you be able to just tell us a little bit about it and why this instrument is needed for the type of observations that you're going to be doing of these large structures in the early universe.
You want to go, Ben?
Sure. Yeah, I can take that. Sure. So as Ekta was talking about, understanding the distances of these many galaxies is very important for determining if they are members of these overdense structures, among other things. And one way to do that, as Ekta was describing, is to make these masks and take spectra, where the light is split into these different component wavelengths. And when you have a spectrum of an object, typically what we're doing is we are looking for various signatures of different elements, which we know correspond to a very particular wavelength or color of light. And so as things are farther and farther away in the universe, they get redshifted, which essentially means that all of the light becomes redder than you would see it if it was right in front of you. And the reason for this is that it's moving away very, very fast, right? The universe is expanding, and so all these very distant objects, we see them moving away from us, and so the light is stretched out. And so by comparing the color of a very specific signature from one or several elements, the color that we observe to the color that we know it intrinsically is, we can measure what that shift is and therefore determine the distance. And while spectra are the most precise way that you can do this, it's also possible to do this with images alone. And so the way this works is that if you imagine what you're doing when you are taking an image of the sky is you are just taking an average of how much light is an object emitting across some range of colors. And we have all different filters that we can put on the telescope that filter out certain colors. And so you know exactly which set of colors you're looking at. And so if we have a candidate structure, for instance, at a very specific distance, we know where one of these elemental signatures will be. What we can do is we can say, okay, we have a very wide filter, which is looking at a lot of light. And within that filter somewhere, there's one of these elemental signatures, which is what we call an emission line. So you can imagine if you were looking at the amount of light from an object, if you say it's pretty flat, and then you see this very small spike from one of these elements, that's what we identify in a spectrum. But if you have a wide band image of the object, and then you also have a very narrow band, which happens to lie, which is sensitive to light where that emission line is, what will happen is the amount of light in that narrow band will appear elevated relative to the average over the wide band. And so one of the capabilities of MOIRCS, or one of the advantages for this science, is that MOIRCS does have several of these very narrow filters available to us. And fortuitously, for the structures that we are looking at tonight, several of these filters line up with where we expect these emission lines to appear. And so essentially the science that we are doing is to say we take these very broad band images, which we already have, and now we combine them with this narrow band imaging, and we look at the difference in color between those two. And that can give us an idea of whether or not a galaxy has this elemental signature at the redshift or at the distance of the structure that we are probing. And so that, I'm sorry, I don't have a nice visual to show that at the moment. I don't know if Ekta or Roy have a nice plot of that. I can pull it up here real quick if you give me a moment.
Thank you, Ben. And we can now also hear a bit of the conversation with Brian and the rest of the observing team there in the Subaru remote control room. Ben, can you give us a sense of what's happening now?
I can try. Yeah, sorry, I'm not on that Zoom concurrently, but the So the first thing that we do when we start, I guess the very first thing when the night is split in half, so we're observing the second half of the night. First thing to do is to change the instrument. If the first half team was using a different instrument on the telescope, there's a transition process for moving to a different instrument. So I believe that has already been completed. But then after that, we have to do a few calibrations. And so this is just making sure we understand very precisely how sensitive the instrument is. There's also other effects that are dependent on the observing conditions, the weather for the night. And so we have to focus the telescope and make sure we understand how sensitive it is, given the current conditions. And so I believe that's what they've been working on recently, and they might be done with that by now. And if they're done with that, then they are beginning the actual science observations, which we're interested in. And so the plan for tonight is, again, to observe in one of these very narrow wavelength imaging filters, several of these structures that Ekta mentioned. And I think the plan is to have observations of, I think, several minutes at a time. It depends a little bit on the filter. But I think Brian may be able to speak more to where we are at the moment with that. I don't know, Brian, if you have a moment. Brian cannot speak. He had his son gave him a cold over the weekend, and so his voice is a bit hoarse. And in addition to that, he's also on the observing Zoom, so he doesn't want to contribute background noise there. But you can see a few on Brian's screen. You can see a few of the observing screens there. I can't see them well enough to tell you exactly what's going on in them, but yeah, they are taking data, and so that is exciting.
Yes, that is really exciting. And thank you for getting us kind of oriented to where we are right now and what's currently happening, Ben. We can put this question out to either Ekta or Roy. Ben mentioned the observing plan. Do you all work together on the observing to develop the observing plan?
Yes. So it starts with actually let me backtrack a little bit, which is that the way that we actually get access to these telescopes and the way that we get our observing time is competitive. So we have to write a science proposal where we say, this is the science we want to do. These are the galaxies, stars, protoclusters, whatever we want to target. This is the tool we want to use. This is how much time we need to get the data. And that's called an observing proposal. And that already has some idea of an observing plan. And every 6 months, astronomers submit their observing proposals for different telescopes. And a committee called a time allocation committee evaluates them, ranks them, and gives out the time to the proposals that they consider the best. So it's not just sitting there waiting for the taking. So we've already, when we've asked for this telescope time, had a good idea of the science we want to do, how much time we need to do it, and things like that. And then as it gets closer, if we are successful, in this case, obviously we were because we were here, or our Japanese colleagues were successful, depending on whether it's Hawaii time or Japan time, another complication that we can talk about later. And then we sit and look in detail, what data might we have in hand from before? How long do we need? How long does it take to move the telescope to read out the camera? Let's say we want an hour of exposure time on a target. We might need 2 hours of telescope time because the telescope has to move, it has to be focused, the camera has to take a bunch of shorter images that we add up later. And so we go through the specifics of planning that with our collaborators and with the specialists at the observatory who know more about the camera usually than the scientists. And they help guide us in creating that plan. So actually, over the last few days or weeks, we've worked out those details of which targets can we observe, when are they high enough in the sky, what other targets would we need, and things like that. So then we create a very detailed observing plan. And in the case of this observatory, you actually create a file with a bunch of commands that says, move the telescope here, take this many observations. So we actually have a file already written that the support astronomers and the observers are running, and we kind of modify that on the fly based on conditions and things like that. We've actually created a full observing program for the evening in advance. And I see Brian sharing, so I'll let him take over, or someone else from the team who's observing to take over.
Let's see,
Hey guys, so I just shared one of the screens that we have up here. We have 8 screens total. We are observing now. We had a problem with the telescope earlier, but everything is, we think, okay now. So this is just a live stream of the images that we're taking with Subaru right now. And Ben, if you don't mind, or somebody just talking like through like very roughly what we see here. It's not spectacular, but we're trained on the Redshift 3.3 structure in D1, and we're on our first pointing, taking our first dither pattern.
Great, thanks, Brian. Yes, so so as Brian said, this is one of 8 screens the observers have available to them. So there's a lot of information to look at and kind of monitor progress as we are observing throughout the night. And as Roy mentioned as well, the process for taking these images is actually to take a bunch of shorter exposures and then combine them at the end of the night. There's a few reasons for doing that. This is more common in these infrared wavelengths that we're looking at because there's a lot of sky background and effects that that are variable. And so we want to be able to subtract those effects out of the images. And so in the center panel there, the one that's, I guess, zooming in and out, you can see there is, it doesn't look like there's a whole lot there. And that's because this is one of these very short integrations. But as you take a bunch of these and add them together, you're able to subtract out background effects and noise and really bring out the individual objects at a much higher signal to noise ratio. And so in this particular screen, you can see one of these galaxies is highlighted there, or a different one now with that green box. And that one that is highlighted is then shown in the zoom in on the top right zoom, or the top right zoom in there. So yeah, that's a fairly bright one there. And so this is an individual galaxy. You can see all the little squares that make up that image. Those are the individual pixels of the detector, the camera. And these are, essentially measuring not only the amount of light, but also you can measure, for instance, the size of these objects, how big they are. And by combining this with many other images, you can derive all sorts of properties from, as Ekta was saying, the distance and the stellar mass of these objects, if they're forming new stars and how many, potentially how old they are. And so there's a lot of information you can get from this. And in fact, until about 30 years ago, pretty much everything we knew in astronomy and all the work we did came from light. That's what we do as astronomers. We study light. How much of it is there? What color is it? These are, in all different types of light. This is how we from ultraviolet light, optical light, infrared light, radio wavelengths. This is how we learn about the universe. And as some of you may know, this has changed a bit in the last 10-ish years with the detection of gravitational waves, which I won't get into in too much detail. But these are somewhat revolutionary in that this is a completely different way to probe the universe. Instead of looking at light, looking at these gravitational wave effects. But that's a little off track from what we're doing tonight. So this screen, for instance, as we keep taking observations, would probably update as a new image comes in. And what we will do then is to compare how bright a given object is in these images to how bright an object is in these other band passes, and from that we will be able to get an idea of the distances to these things. So that's a little bit of an overview of what we're seeing right now. On the left image there, you can see there are those two axes, and so that's just telling you the direction essentially that the camera is or the angle that the camera is pointed. And so you can see the yellow axes there give you the y and x axis of the image, and then the blue arrows give you the cardinal directions relative to those. And so your first inclination may be, well, east is the wrong way, right? If you look at a map and north is up, then east is to the right. But actually, if you are looking up at the sky, that's reversed. East is to the left if north is up, and west is to the right. And so this is something it still makes me hesitate when I'm now looking at a map or trying to figure out directions in real life. I have to switch from astronomical thinking about which way is east and west to on Earth, which way is east and west. So that's fun. But yeah, that's probably about as much as I can go into with what we have here at the moment. I don't know if Ekta or Roy or anyone else wants to add anything.
That was brilliant, Ben. Thank you.
Brian says he's going to switch screens. Perfect.
Yes, that's going to be great. And maybe Ekta, maybe you could answer this question here we have from Remus. Remus is asking, could you give us an example of a science proposal to perform observations for extragalactic astronomy?
Yes, I will answer that. That's why I got one of the proposals ready, but I think I can answer that maybe after we talk about the screens, because I would like to also share my screen and kind of walk through different parts of the proposal. So maybe we can go to that question after this.
Brilliant.
Okay, Ben, do you want to continue?
Sure. Yeah. So yes, this is another data screen here. And oh, yep. Okay. Thank you, Brian. Cool. So yes, this is now we more than one image. This is combining some of the images that we've already taken this evening. And so I think someone maybe mentioned this already earlier. When we're pointing at the sky, we take an image. But then it's also important that we do a very small shift of where we're pointing to take other images. And so what that does is enable us to, when we kind of average over all those images, that allows us to correct for any detector effects, any sky effects, things like that. We can characterize the noise in the image a lot better, and therefore understand the objects. And so that's kind of what you're seeing in these images here. So the image kind of in the center, I guess, but on the left of that one panel has the, I guess, blue square around it. You can see that you have almost two copies of every object, right? You have a white one, and then you have a black one to the left of it. And so that's essentially taking these two images that are slightly shifted relative to each other and subtracting them. And so what that will do is for any region of sky where there's nothing that's detected, it just looks kind of noisy, maybe like a TV screen on static. I don't know if that means I'm dating myself now, but most of the image looks like that. And then you will see these regions that are very obviously different, that have these highlighted sources. And that's where galaxies are, or stars, if there are stars in the field. And that's what you're seeing here. And you can see that a new set of images just popped up. So that means that a new set has been processed, which is very cool. And then you also see that a green box is highlighted or was highlighted on the right. That's just selecting an object I believe, to go in the plot on the upper left of the screen. And what that plot is showing is just the light profile of the selected object. So the x-axis is the distance from the center of the object, and the y-axis is how much light there is. Right? And so one reason to do this while you're observing is to get an idea of what is called the astronomical seeing, which is a characterization of how good the observing conditions are. And so what happens when you are observing, at least from the ground, you don't have this problem in space, but when you're observing from the ground, the atmosphere, of course, is between you and the sources that you're interested in the distant universe. And so as light travels from them through the Earth's universe, it actually gets scattered, right? As it interacts with different pockets of air, different temperatures and pressures, and these kind of different bubbles of air will scatter the light slightly differently. And so if you have a source in the sky that is a single point, that light will actually get spread out to some width. And I guess, noisier or messier the atmosphere is when you're observing, the more that light gets spread out. So of course, from an astronomy standpoint, we would like all that light to be concentrated in a very small area. That gives us a better signal to noise ratio. So we're able to do better science when that light is more concentrated. And so the plot on the left is essentially showing us how spread out that light is. And so I think Brian said in the chat, his estimate of the astronomical seeing right now is 0.4 to 0.5 arc seconds. I'll just say that that's very, very good, quite a bit better than we were expecting given the forecast for tonight. It looks like Roy has put a nice article in the chat as well, if you're interested in reading more about seeing and some of the ways that astronomers deal with it. So I will stop there. And I don't know if Roy wanted to say more on that.
No, actually, Ben covered it, and if you wanted to go to the article, you can read more about it. I actually will add that one of the reasons we go to space is that we don't have atmosphere where Hubble Space Telescope or James Webb Space Telescope are, so they don't experience seeing. They get the image quality at what's called the diffraction limit, which is a physical limit to the quality of the images you can get, to the resolution that you can get. That depends purely on the wavelength of light you're looking at and the size of your telescope. So if we make it, one reason we make bigger telescopes is to collect more light to see fainter objects, but also to see more detail. So if I make a telescope, if I double a telescope's diameter, I can see 2 times finer detail, forgetting about the atmosphere. We do have ways to correct for the distortions of the atmosphere called adaptive optics, and the article I posted in the chat talks about that. But that only works over a very small part of the sky, smaller than what we're observing with this camera, and only at certain wavelengths of light where we have the tools to do it. So we're not using it with this camera in this case. And then Jamika put in a question about how does targeting the ionized oxygen from galaxies in these structures help with mapping the objects. So I don't know if Ekta had the proposal, if she was going to show the proposal for this specific science program, but the reason we're using ionized oxygen is because it's relatively prevalent in galaxies that are forming stars. It emits light at a very specific color or a very specific wavelength, which we measure, like water waves are measured in wavelengths of meters or feet or whatever. Light waves are measured in much smaller units, nanometers, microns. In infrared light, we often talk about microns as the wavelength of light we're talking about. But this ionized oxygen emits at a specific wavelength of light. The farther away a galaxy is, the color of that light shifts. It's what's called redshift. That could be a whole other discussion we can have. So, but if the galaxies are the specific redshift that we're targeting, then this wavelength of this specific emission feature in light is shifted into a filter that exists for this camera. which picks out basically light only of the wavelength we're interested in. And galaxies that are at other redshifts but emitting this light, we don't see them because that light is not in our filter. So the galaxies that are at the right redshift for us to be interested in will look brighter in this filter than galaxies that aren't at this redshift. Now, there might be galaxies emitting other colors of light in these with different emission lines that will be at different redshifts that will also appear bright in our filter. So that's a source of confusion. But if we have the right combination of filters and different emission lines, it's kind of like finding a set of fingerprints that matches without having to break the light up completely into a spectrum. So that's a kind of a trick we're using to sort of narrow down which galaxies are likely to be at the distance of the big structure that we're looking at. And an excellent question about the full moon high in the sky. One, it doesn't matter so much because we're using a narrow band, but it also doesn't matter because we're looking in infrared light. And in infrared light, it's the warmth of our own atmosphere, the warmth of the mirror, and other things that actually dominate over the moonlight. So we actually have to take relatively short exposures in infrared light because overall the sky is bright. The moon does matter some, but not as much as in visible wavelengths of light. So in fact, if you look at a telescope schedule, what you will see is that when the moon is up, when there's a bright moon up during the night, all the telescopes have infrared cameras on them. And when the moon is dark for much of the night, when we have a, less than a quarter moon, you'll see optical cameras on the telescopes because they're much more sensitive to the moonlight.
I'll also add in that we're pointing at a very small region of the sky, which is not particularly close to the moon. So that also helps. We don't get direct moonlight into the camera either.
And so with these different kinds of filters that you can use, I imagine that sometimes throughout your observations as the sky dynamics change, are you able to, do you have to sometimes switch filters when you don't actually plan to ahead of time? And how do you deal with that?
Sorry, I was sending an email. Can you repeat that, or if someone else wants to take it?
Oh, sure. Just since you were Roy was talking about the filters and in relation to having the full moon using a narrow filter. And this is a question to all of you. The sky and the weather is so dynamic, and especially on Mauna Kea can change unexpectedly. And so my question was, is there sometimes a need to have to switch filters unexpectedly it's not a part of your observing plan? And if so, how do you deal with that kind of change?
Yes, that's an excellent question. Thank you. Yeah, so there are generally a few ways we go about this. First of all, when we're getting close to our observing, we will have a forecast, and so we can get a general idea of what the weather is planned to be. And so almost no matter what, we'll usually have some backup science goals. So if the weather is so bad that we can't observe our main science goal, we'll have a backup target, maybe something that's very bright or more easily observable, that we can try and get data on. Of course, if there's rain or something like that, we're not going to be taking any data, unfortunately. But yes, yeah, that's a great point. We always have several science goals that we can pursue. We have the main one, and then if conditions don't allow it, we will have other goals. And so those can be other objects, they can be other filters. It really kind of depends what you're interested in and what the weather looks like. Yeah, that's a very good point. Thank you.
And sometimes what also happens is you take observations, and as you are taking observations, the weather isn't too bad that you're gonna kind of move away, but it's just kind of, maybe light clouds or uh, humidity or something. But for some reason, when you look at the observations, they are not as good as what you expect, right? So then what you can do is, instead of like, let's say you were planning to take observations of that object for like 1 hour, so then you say, oh, the conditions are worse, or you know for whatever reason the objects don't look as bright as what we expect, so then you can take like even longer observations and add them together. So sometimes we also allow that window. And sometimes what also happens is, if you have some proposals that allow you to take observations kind of on multiple nights, so then what we can do is we can kind of take test observations, right? And then we can say that, hey, for this kind of objects in this kind of weather, we initially thought that 1 hour would be sufficient, but now let's kind of take 1.5 hours of observations or 2 hours of observations. So depending on what kind of instruments you have, what kind of telescopes you have, and what kind of observing nights you get, and also what kind of telescope you have, because in some telescopes what happens is you give them all the information and they take observations for you, versus in some other for some other telescopes, like if you're using Keck telescope, then you control the instruments, and you can decide that, hey, I want to take longer observations on this target, or if I want to move on some other target. And in case of Subaru, you tell the observing team that, hey, we want to switch to this target. But for some other telescopes, you don't get that one-to-one interaction while the observing process is going on. So you just have to provide them list that if the weather gets worse, switch to this or keep observing this. So yeah, it also it depends on many different things. But if you have control, you can kind of make this kind of decisions, either moving to different targets or continuing.
Yeah, and so there are trade-offs to those different observing methodologies the different observatories have, as Ekta was describing. Yeah, as she said, something like Keck, it can be very nice because if the weather changes, or if your science goals change, maybe you had some other data come in that changes what you want to explore with your time on the telescope, you can do that to some extent. But the problem with that is that if all the nights are assigned, and so if, for instance, you have a cloudy night or it rains or something like that, and you can't get data, you lose the night, right? You don't get it back. You have to apply again next time. And so that's the trade-off there. Whereas something like the Gemini telescope, which is actually where Brian works, they do what's called Q observing, which means all of the proposals which have been accepted for time get put in this queue, and they're ranked by how highly rated they were by the committee. And they all also have a series of weather conditions which are acceptable to the scientists for the observations. And so the queue just gets run as the semester goes. And so if there's a bad night and you need good conditions for your observations, well, your science won't be observed that night, but it will still be in the queue. And so on a future night when the weather is good, then it can be observed. And so you don't get the flexibility with being able to change your observations, but you are more likely to actually get some data. So there are trade-offs with these different methods.
So Roy, Ekta, Ben, Brian now has up the weather monitors along with the telescope status display. Can someone give us some insights into what we're seeing, maybe starting on the left with this part that says tracking?
Yeah, I can talk about that. So what happens is, as you might have seen during the night, the objects in the sky seem to be moving, right? Seem to be rising and then setting, just like the sun seems to be rising and setting. So what happens is, if you want to continuously observe one object, but it will kind of move on the sky, right? Because of the rotation of Earth. So what you want to do is you want to continue staring at the same object, right? But since it's moving, which means that you will have to move the telescope with it, right? And so that's what we kind of call tracking, that as the object is moving, you are kind of tracking it and you're continuing to observe it. Because if you don't do that, then, it will kind of, when you take picture of something that's moving and it looks kind of this blurry and fuzzy and just kind of like a streak. So you will kind of see streaks if you don't track it well. So what you see on the left screen is that we are kind of tracking the object. So there is not much there is not any offset because we are kind of tracking it well. And on top bar, you also see the location of the object that we are targeting. So it's RA deck, it's azimuth, and then you also see air mass. So kind of how from surface, how high are we looking? And what else do we see here? Widescreen CMD data. Okay, so then we see the, in the third column, we see the proposal ID, instrument, and then we see the object name that we are given. And then there are different limits, because what you also have to keep in mind is the telescope is this, huge object. So you can't just kind of randomly rotate it in any direction. There are lots of options, but at some point you will reach the limit in different directions, right? If the object goes too low, you can't observe it. Similarly, the telescope itself also has some constraints. So there are these different limits that you see here. And so it's good to keep that in mind. And then, yeah, I'm not sure what the other stuff is. Then we also have the wind speed. So you have to keep an eye on that. If the wind gets too high, the telescope can get damaged. And then we have temperature, humidity. So everything is kind of looking good. And then I don't know what the catwalk sensors are for, but maybe somebody can comment on that.
Yeah, thank you, Ekta. Yeah, Ben or Roy, can you comment on these sensors here?
Yeah, so sorry, message from Brent. Okay. Yes, so as we're looking at those catwalk sensors on the right, so these are environmental sensors looking at what the conditions are outside. And so, of course, you don't want those to be inside the telescope dome. You're interested in what the conditions are outside. And so what we have there, so this is on the very right column, we have from top to bottom the outside temperature, the relative humidity, and the dew point. And so the reason that, so the temperature, of course, is important because if the temperature, I guess I'll say these are all interrelated, right? And so what we don't want to have happen is for there to be any condensation on the telescope itself, right? And so obviously if there's rain, then liquid gets on the telescope. That's not good. But you could also have liquid get on the telescope or the detector if the relative humidity is very high. And so what we see very nicely is that the relative humidity is pretty low. It looks like about 13% or so at the moment, which means that the air is pretty dry. And so that's good not only for making sure that water doesn't get on into the telescope, but also water is one of the things that when it's in the atmosphere can perturb the images and increase that astronomical seeing value. And so that's another reason why telescopes are often built at the tops of mountains or sometimes in very dry places, is you want to minimize the amount of water vapor in the atmosphere overhead because that gives you better observing conditions. Yeah, and then there's also, yeah, as Ekta said, there's the wind speed there as well. If the wind speed gets too high and it's in the, actually we'll call it the wrong direction, that can actually cause the telescope to have very small vibrations, which then, similar to what Ekta was saying about not tracking properly, that makes your images a bit more blurry. And so if there's too much wind, if there's precipitation or if it's too humid, all of these are things which can cause observations to be stopped either for the entire night or for a temporary period. And so, as Brian is saying in the chat, it's very interesting. And as Jamika mentioned earlier, the conditions are very dynamic and very localized up near the summit of Maunakea. So the Gemini North Telescope is also up near the summit. It's a few hundred meters away from the Subaru telescope, which we are using here. And as you'll see in the chat, the wind speed measured by Gemini is 50 miles an hour, and the wind speed measured by Subaru is 10 miles an hour. And that's not a measurement error. That's actually a real difference in wind speed just based on this small distance apart. And so a small locational difference. And so that speed of 50 miles an hour is strong enough that Gemini is unable to observe. And so if you had time on Gemini tonight, this is when you're happy that it is in fact Q observing, because you can still have your data observed later in the semester. Whereas if it was, the Keck telescope, for instance, and there were 50 miles per hour, you'd have to reapply again in the future for time.
Brian, what's the typical limit when you guys stop wind speed in terms of wind speed? Maybe you can type.
Yeah, I don't remember offhand what it is, and I don't know if it varies from
Yeah.
telescope to telescope. There's also some depends. Yeah, so Brian says for Gemini is 50-mile-an-hour gusts is their limit. I will say one other thing that can also happen, which I've had the unfortunate experience of having when I'm observing on Keck, is that if you've had a big snowstorm or ice storm in the recent past and there's still ice frozen on the dome, if the winds get above 15 miles an hour, there is a small risk that the wind will actually blow some of the ice into the dome. And that's obviously not good. And so on those nights, if the wind gets above 15 miles an hour, then you can't have observations. So yes, yes, while the snow can be beautiful, it can be detrimental to observing conditions. So yeah, another thing that can be very nice when you have Q observing. Yeah, and as Brian says there, yeah, there's a method in place for determining once the wind goes above this limit when you can come back and start observing again. We're concerned about these wind gusts, not the average wind speed, but how gusty it is. And so if yeah, there you put in the chats, right? So once you reach the limit of 50 miles an hour, you need a 30-minute period where the wind is not above 45 miles an hour before you can start observing. You can open the dome and start observing again. So it's maybe similar to if you've ever been in a swimming pool and there's a lightning strike nearby, they'll get everyone out of the pool, and then you have to wait, half an hour until you can get back in the pool without there being any more lightning. And if there's, a lightning strike 20 minutes later, then the clock restarts and you have to wait another 30 minutes. And so it's similar with these high wind speeds for a safety precaution.
Brian put in the chat that once the wind speeds hit a certain amount, hit a certain speed, and then they decrease back down to an acceptable level, there's still a certain amount of time that you have to wait before getting back to observing. Is that time that you wait to get back to observing, is that taken away from your observing time, or do you get that back in some way?
So some of this depends on the telescope you're at. So for instance, for us, we're assigned this night. If the weather was bad all night long, it's gone. And let's say we're assigned 2 nights, that's all we got from our observing proposal this semester, and the weather is bad, we get nothing, and we actually have to write a new resubmit or write a revised proposal for next year and hope that the weather is better. And it could be the weather, it could be that the telescope breaks, it could be that the camera breaks, could be all of those have happened to us. Some like the targets we're observing now are more winter targets. There are targets that we observe a lot in January when the weather is, even on Mauna Kea, the weather is worse. So we've had targets to where we've proposed 3 or 4 years in a row and gotten no data. So that just happens. Q observing has the benefit that it moves around the weather more flexibly, but even there, if the weather is bad, unless you're one of the highest ranked scientifically proposals, you're not going to get your data or only a small fraction of it. If as Brian's writing there, I mean, there have been issues. Subaru has had a issue with their primary mirror. Gemini had a issue with its mirror when there's been earthquakes, storms, stuff. Telescopes have gone down for weeks or even months at a time, and then you just, it's. Yeah, I mean, you see Brian's writing there. They had an error in the coding that they lost 45 minutes. One of my first times observing at Keck back when I was in grad school 25 years ago. We were up at the summit and we were observing, and on the keyboard that the telescope operator was using, the Q key got stuck in the down position, got mechanically stuck. And it sent like 1,000,000 letter Qs to the telescope control system and crashed the whole telescope. And we lost a whole hour of telescope time because the keyboard broke. So, and an excellent question about data available to the public. Yes, almost every telescope has an archive of data. The data does not just look like pretty pictures, though. It needs a lot of processing to be turned into useful data. But it is available. Subaru has a data archive. It usually becomes public 1 year, 2 years, depends on telescope and the country's policies. But yes, and we actually use a lot of archival data in our work. So like Keck Observatory has COA, the Keck Observatory Archive, and you can go get all the data that's more than a year old from Keck, if you know what to do with it. And since I've been in Ekta and Brian on, I'm going to say goodnight because I have to get up in 4 hours to take my kids to school. So thanks everyone for joining. I'll probably see if anyone joins tomorrow night. I'll probably be on for some of that as well.
Good night, Roy. Thanks.
Much, Roy.
Hey, thanks, Roy.
Aloha.
Aloha.
So we have a countdown that's happening here. Is this it says time to completion? So I assume this is this round of observations here.
Yeah, so you see on top left, so there are some rows that are green and then some rows that are black. So basically it's taking the observation. So you see the black, first line in the black is like MCS and then 8993. So it's taking that observations, and once it's done, it will put its information in green. So what we are seeing in the screen is on the left, bottom left, right? So you see some file with lots of different rows and it says setup field and lots of other things. So that is the file that Roy had mentioned, right? So that's the file that Roy had mentioned that contains kind of detailed instruction for what kind of observations we want to take for which field and all. So you see the green line. Oh yeah, so you see, you just saw on that top left that the line turned green, and then now it's moving to the next line. And now, so the next observations are taking place. So then for next observation, it's like, 140 seconds or a little over 2 minutes. So I was saying that in the bottom left, you see the green line highlighted. So that's the line that's currently getting executed. So basically you have get object, which means it's taking observations, and then you have like exposure time. So what's the duration for which you're observing that target? And this is for individual image. So each green line, it's for each green line, it's total exposure time of around 150 seconds. And then it has like a NDR, so 4 repetitions, and then dither number. So dithering is when you move slightly and then take observations again, and when you move slightly again and then take observations again. So there are total 9 ditherings, and it has some other information about dithering. Um, so yeah, this is the file that Roy was mentioning. So this is the file that we have created and we sent to the Subaru team that's currently taking the observations for us. What else do we have? And then we have logs to keep log of what is getting done. And then we have time for completion, and then in the left we have information about the telescope, so the focus, rotator angle, and information about dome flat. We are not taking dome flats right now, so that we don't have to worry about that, but we use kind of flats um, to kind of it's kind of like when you close your eyes and you still see some residue light. So what happens is in the instrument itself there will be some what do you call it, basically in the instrument itself there are some impurities. If you provide uniform light to it, not all the points in the instrument are going to produce the same value, right? Ideally it should, but because it's a mechanical instrument, and it's the kind of real life, so it won't produce like some. If you provide uniform light of around 100 in some unit, some instruments will say 99.9, some instruments will say, sorry, some parts of the instrument will say 100.1. So what you want to do is you want to take that values and then kind of correct for that, right? So that's when we kind of take dome flats and we kind of use the uniform ish light from the sky and take those kind of observations that give us information about the instrument that we can use for our own observations to better calibrate the observations. Okay, that was a bit too much detail, but hopefully that gave you some idea. um, yeah, because you do have to see in theory, when you are working with like mathematical theories, you work in ideal world, but when you are taking actual observations, you have to deal with like the imperfections of the instruments. Not only imperfection, even the limitation itself, right? Because each instrument will have its own limit of how accurately it can measure. Then each instrument will have its own kind of non-uniformity. So there are lots of things that you have to take into account, and then correct your observations for that if you can. Okay.
Yeah, so we're on the top left is showing the dither pattern or the exposure sequence. So I don't know if you went over this, Ekta. Sorry, I'm trying to juggle like multiple zooms here and everything. But yeah, so each one of these numbers here in the line, the black ones. So 2 of these makes an exposure because we have 2 different chips on our detector. And so once, I think you mentioned that they turn green at some point, Ekta. Sorry, one sec. Sorry, can you repeat? Yes, I can check. Hold on. It was Teddy, it was all over the place. It was from 0.6 arc seconds all the way to 1.6.
Oh, okay.
Yeah, so it's okay. We're not at 1.6 yet, I don't think.
Yeah, we'll keep going and
Oh, come on, we're 1 arc second or so. Yeah, so I think we can keep going, no problem. Or do you want to do a quick focus?
well, this is not focused, right? It's partly focused, but
It looks like astigmatism to me. Yeah. But it does look like there's some astigmatism in the image. Happy to keep going though. It's fine. We can just keep it. We can do another one, and then we can focus afterwards. Yeah. So sorry. Yeah. So we're on our last sequence or last image of this sequence. So we basically dither. Maybe actually, I don't know if you guys talked about a dither pattern or what it is. Or, okay, good. And so this is the last image of the dither pattern. And then we're gonna do a very slight shift even away from this dither pattern to another dither pattern. But we're having the images are getting blurrier, and we don't know why that is, whether that has to do with the instrument or that has to do with the sky or that has to do with the fact that we're now going lower in altitude, and so we're looking through more atmosphere. And so we're debating now whether to focus the telescope. So basically to figure out how to correct for any focus aberrations. We definitely do see some astigmatism in the images, and so that is potentially correctable with the focus. But the downside of the focus is it takes about 10 minutes or so, and that's time we could be spending taking observations of the actual targets. So it's a debate. Do we want to do it? Do we not want to do it? I don't know. So we'll see. They're gonna make a decision. I said what I thought, but I'm not driving tonight.
Brian, do you, if the image is up on that screen, do you want to share the screen to show us the estimation?
Yeah. Yeah,
Or is it
I can
gone?
show them. Okay. That's astigmatism. It's not so bad in that image, actually. It's not so bad. So in the previous image, we saw basically what should be a circle, which is a star or point source, could be like a really far away galaxy. And instead of looking like a circle, it looked like an oval like this, and it was pretty elongated. So I think we're just looking through a lot of atmosphere right now, and it's probably dancing around and it's messing with the focus of the telescope. So I think we're probably just going to keep going. Yeah, we decided to just keep going. I think that's the right move. It looked pretty bad before, but now I think it's the right move.
Mm-hmm.
So we're gonna do I don't know if you guys have talked too much about the targets tonight, but we're gonna do the last set of exposures here. So one dither pattern here. I think it's a 15-point dither pattern. And then we're gonna go to a standard star. So maybe you guys can talk about like why we would do that. And then this is actually where the air mass curves meet for the D1 field and Cosmos. So we're kind of taking a break to calibrate everything, and then we'll move over to Elantari after that. So I think we'll be the tether sequence will probably finish the Shadow of the Scientist session. But tomorrow night we'll be moving targets. So for those of you who get to come tomorrow night, to see that. But we'll have other sessions in December too, where we'll be moving around the sky.
Yeah. Thanks, Brian. Yeah, so just to reiterate or go into more detail on a few of the things Brian was saying. So he's talking about the air mass curves for our different targets. So as Ekta was saying, right, and as you know, throughout the night, a target will rise in the east, it'll move across the sky, and it will set in the west. And if the target is directly above you, you are looking through essentially the width of the atmosphere to see that target. But if a target is more towards the horizon, you're actually looking through more atmosphere, right? You have the Earth, and then if you imagine the atmosphere is kind of an annulus around the Earth, right? If you are looking straight up, you go through the width of the atmosphere. But if you're at an angle, this is more than one width of the atmosphere, if you will. And so that's characterized by the air mass number. And so the higher the air mass number, the more of an effect you get from the atmosphere, which is not what you want. So if you can observe things that are directly overhead, that's a little bit more ideal from an atmospheric perturbation standpoint. And so we have two different targets that we're observing tonight, which are not in the same place. So as the first target has been moving across the sky, now the second target is starting to rise. And so in a little bit, we're going to switch from targeting this one over to this one. And so we've, done some modeling, or we can see when the air masses for those two targets are the same. And when the air mass for the second target starts to become less than the air mass for the first target, we will switch to that target to optimize our science returns. And so that's another consideration when we're making our plan for the night is, how long can we observe a target before it gets to such a high air mass that the returns are fairly small, and it's not worth observing that target anymore.
Ben, is adaptive optics in any way helpful in dealing with those, looking through those higher air masses?
It can be, yes. So adaptive optics is, again, so Roy posted an article earlier about adaptive optics, but just, I guess, to back up on what adaptive optics is, as we've mentioned, right, the atmosphere through which you're observing to see your science target is constantly moving. You can think of it as lots of different pockets of air that have different temperatures and pressures. And those, as light from your target is passing through those bubbles, it gets perturbed and spread out. And so if we know exactly what those pockets and bubbles of atmosphere look like and how they perturb the light, and we can correct for that, then the observations become much more efficient, and it's closer to what you would get if you were observing without an atmosphere in the way. And so what adaptive optics does is to shine a laser into the atmosphere and then essentially observe that laser, right? Well, there's a few different ways to do it. So that's with what's called a laser guide star. So you shine a laser up and you measure how the light from the laser is being perturbed. And you do this very quickly, and then you feed that information to these little perturbers on the mirror of the telescope. And so you make these slight perturbations to the mirror to correct for the atmospheric effects, which is very cool when it works. And so, yes, yeah, you can, the adaptive optics definitely can help with that. So you can do it with either a laser, or you can actually do it with a real star as well, because a star is a very small point source. And so, intrinsically, it's going to be very small. It's not like a galaxy, which could be elliptical in shape, and it has some intrinsic size to it on the sky. A star is point-like. And so you can observe that star instead of the laser and measure how that light is perturbed and correct the telescope that way. And so adaptive optics can work for that. The limitation of adaptive optics, which I think Roy may have mentioned earlier, is that that correction is only valid over a pretty small region of the sky. And so as you get farther and farther away from either the laser or the star that you're using to correct the mirror, the bubbles in the atmosphere are changing. They're not the same ones. And so the improvement that you get is localized to a fairly small area close to that laser or star. And so in the case of the observations that we're doing tonight, the field of view that we're observing is quite a bit bigger than that correction region would be. And so there's the current instrument is not compatible with adaptive optics, partially for that region, because it wouldn't really give you the effect you want. Now, if you're doing spectroscopy, as Ekta was talking about earlier, and you're maybe only looking at a single target and getting a spectrum of that, adaptive optics is great because you have this one object and it may be very close to either the laser or the star you're using for correction, and then you can take out the atmosphere very very effectively. So yeah, adaptive optics is great, but it doesn't work for all observing programs.
So Brian has shared in the chat that as the sky gets too bright to actually do other aspects of your observing plan, that you'll be doing dome flats. For those who aren't aware of what those are, could you talk a little bit about that, Ekta or Brian, Ekta or Ben? And then what else do you do towards the end of the night as you're wrapping up your observations?
Yeah, so yeah, that's a good thing to talk about as well. So as we've mentioned today, a very important thing with these observations is to make sure that we understand, as Ekta was saying, how different parts of the detector react to light, or how they report the amount of light that is being observed. And there can be differences over the face of the detector. There are also differences with how different parts of the instrument respond to changes in temperature. And so understanding all these pieces is important for getting the most accurate and precise scientific returns out of our observations as possible. And so part of this are what are called dome flats, or in general, flats. You can also do flats on the twilight sky. But essentially what this is you are observing a source that is uniform, roughly uniform in brightness, and seeing how the detector responds to that. And so those little perturbations that Ekta was talking about, if you have 100 photons and part of the detector measures 101, part of it measures 99, you can then correct for that by knowing the intrinsic brightness of this source. And I'm actually not sure what it's like in Subaru, but it depends a little bit for different telescopes. For the Keck telescope, for instance, there's an actual region on the inside of the dome that we're able to illuminate uniformly, and then we just point at that. So we know that the surface is uniformly illuminated, and then when we observe it, we can see all these little perturbations due to the detector imperfections. And so we will be taking those observations, when it gets too bright to keep observing. But yeah, as long as we're able to keep tracking and keep observing science targets, we want to do that for pretty much as long as we can. And that is one nice thing about infrared wavelengths as well, is you can usually go a little bit longer in the morning than you can with optical wavelengths, because as the sky gets brighter, that's being illuminated by the sun, which is brighter in optical wavelengths. It's not as bright in the infrared. And so for infrared observations, you can usually go a little bit longer, get a few extra minutes out of it, which is fun.
And one thing is also with dome flats, because like Ben mentioned that, you basically eliminate some part inside the dome with some uniform light. What it means is you can do it during the day, right? Because you can just close the dome and then illuminate some part with some artificial light. So you don't have to do it during your precious night time of observing. So that's why usually, for some of the telescopes, depending on when in the observing night, your targets are gonna get observed. Sometimes you can take dome flats even during the afternoon or in the morning, depending on the schedule. So that is quite advantageous. And I would again emphasize that, no matter what, so even with dome flights, for example, we are saying that we are eliminating the area with uniform light, but of course there will be, intrinsic some non-uniformity with the source. So you are not gonna get like, there is nothing that's like infinitely precise, and infinitely controllable, right? So there will be very minor non-uniformity in the source uh, luminosity itself. So you have to keep that in mind. I mean, you can't control for that, but just something that you have to keep in mind, that your instrument is going to have some error bars and then some non-uniformity, and your light is going to have some non-uniformity. So everything that you measure is going to have some error bars and some non-uniformity. So you have to just keep that in mind. But usually they are small enough. It's like, if I measure your height, right, and I say, Jamika, I'm just saying, just like 6 feet. I'm not saying you're not probably for 6 feet, but for example, it's like 6 feet and 2 inches. So that is sufficient enough. But if I say like 6.6 feet, 2.2.222 inches, so that is still like, depending on which instrument if I'm using, I can get more precise, and then there will be some error bars, right? So uh, that's also something you can keep in mind. Like even when this kind of telescopes, people are designing different kinds of instruments, there is again like trade-off of like how precise you want that instrument to be, and what's the resolution you want. Do you want to be able to resolve like 100 nanometers of light, or do you want to be able to resolve I don't know, 10 angstrom of light? So there are lots of different trade-offs that takes place when you're designing the instrument itself, and what's your science target and all that. So yes, a very complicated world of measurement. But I will go back to the proposal part actually, because it's kind of related to that. So what it means is that different kinds of telescopes have different kinds of instruments, right? And different kinds of instruments are gonna give you different kinds of precision and different kind of information. So when you're submitting some proposal, you have to kind of look at like, I may want to observe some alien on Mars or something, uh, but then I have to check like, oh, is that alien is gonna emit light that is strong enough that my telescope can observe, right? Is it gonna be, uh, is the light strong enough? Is the size of that light like, big enough that I can resolve? So similarly, if you if you're submitting some proposal, you have to look at like, what is the capability of the telescopes that you are observing, that you are submitting the proposal for. And then you also have to keep in mind like what's your science goals. And then you have to, when you submit a proposal, you have to first convey like the importance of your science, right? Why whatever object you are proposing. For example, in our case, we propose to look at the galaxies that could be potentially members of the structures, that will allow us to better characterize the structures, and then also kind of look at, for example, the star formation rate, density, and other properties of galaxies that could have been affected by this environments of the structures. So you have to convey that your science is kind of interesting enough and it's important enough. Um, and then you have to convey that, you have to ask that, hey, I want X amount of time on this telescope using this instrument. So for example, so for some galaxies, you can, depending on what kind of galaxies they are, you have to run some simulations that, hey, if my galaxy is this bright and if I'm using this telescope, it's going to take me this many hours to observe a galaxy like that. So many telescopes actually also provide this kind of softwares where you can put like some information about your galaxy, and then it will calculate that, hey, if you want to observe this kind of bright galaxy using this telescope, it's gonna take X hours. So it will give you some idea about, if you have to propose for 30 hours, if you have to propose for 12 hours, and then you can kind of again make judgments that, hey, if I want to observe like 12 different fields for 1 hour? Will that give me sufficient time to observe the galaxies that I want? Or do I have to, do I need so much observations for just one object that I will need like 12 hours on just one object, right? So there is again that trade-off. So you have to justify your science case, then you have to justify, the time that you are proposing for. So you have to give like technical description of uh, which instruments you want and how much time you want. And then depending on that, the committee can decide that, hey, for example, if you propose 4 different fields, and the committee can say, no, you can do this science in 3 fields, and we are just going to give you this much time. Or if your case is strong enough, the committee can give you all the time that you requested. So the proposal needs to be strong enough for science. It needs to properly justify that the time that you are requesting, and then you also have to provide different technical description of what kind of observations you want.
Thank you for those insights, Ekta and Ben. So in this last 5 minutes, I am very curious to know first what's going on the screen here right now. Is this good? Is this better image quality than before? And then secondly, how can we find out and follow your research besides joining tomorrow's session and sessions in December? I believe maybe Ekta, you were showing some slides from a paper that I think I saw Ben's name on, maybe your name on as well. We'd love to follow up your research. So what are we seeing here, and how can we find out more about what you're doing? Okay, I see links in the chat. Yes.
Yes. So I put link to our website that shows you different studies that our group has carried out. So it includes, the discovery of the structures, along with how the environment has affected the stellar mass of the structures, how it has affected the AGN or the black hole activity, and also the star formation rate density. So many different studies that our group has carried out. You can find it over there. Maybe in some other session, I will be happy to go through some of them. But yeah, and of course, we will be organizing many different shadow sessions. You are free to welcome us. Sorry, you're free. You're welcome to join us for the shadow sessions. And apart from that, I believe that the website also has the contact information. So if you have any questions, you can reach out to us. And if you click on the pictures, it will lead you to paper, and the paper also has like contact information of the individual authors. So if you have questions about particular study, you can also reach out to us. And I think that's
Yeah, I'll just say the link that I posted, this is maybe more if you're very keen on astronomy, but this is a search of essentially astronomical publications. And so you can use this website to search for papers by a certain author, or published in a certain year, or papers with certain terms in them, etc. One thing that has been pretty nice from a public perspective in the last few years is a lot of astronomical journals are moving towards open access. And so what that means is that in the past, the more traditional model was that researchers would publish a paper, and the journal would then charge people to subscribe to that journal, essentially. And so universities would subscribe, but if you were a member of the public, that subscription might be pretty expensive, and maybe not worth it. And so something that's happened in the last few years is a lot of the payment is essentially changing. And so these journals are now, for the most part, the published articles are open to the public, so anyone can view them. You don't have to have a subscription. And so for many of the articles on that website, and especially the newer ones, if you find an article, you can download the PDF of it and read through it if you want, or email the authors and ask questions about it. And I'll just say that I think most astronomers will probably be pretty happy to talk about their research if you do have questions. So please reach out.
Thank you so much. I will definitely be reaching out, especially since we are grateful and thankfully we'll have more sessions with you all, not just tomorrow or later today, but also in December. And I also appreciate you mentioning, I believe, Ekta, that we could click on the image, or maybe that was Ben. We could click on the image and it takes you to the paper. Perfect. Because I was just going to ask, how do I get the link to the paper where those images came from? And you answered it right before I asked it. So perfect. Well, we are at our time limit for this session. I'm going to drop in the chat here a link to our session later on today. It'll be at 8:30 p.m. Hawaii Standard Time. And the upcoming session will be our very first one that's in both Japanese and English, primarily in Japanese, but those who are, if you're an English speaker and you want to join, you are very welcome to join us in that session. I'm going to drop the link here right now, just how you registered for this session. You submit that form, you'll get a Zoom confirmation email with your link. And so when you do that, you'll be able to pop right on in and get to engage with some other people in the session from Japan, which is very exciting. And I see Brian there. We're at the last 30 seconds of this session, Brian. I know your voice is kind of going away from you. Do you have anything you'd like to share before we wrap up?
No, I'll just say thanks a lot to you and Ekta and Ben and Roy for an awesome session, and for everybody for joining. And I hope to be able to actually talk tomorrow, if anybody joins tomorrow, let's see. But certainly in December, so when we have several more open sessions. So looking forward to it, and hope that we can bring you clear skies in December as well.